The Boötes Void sits within the broadest pattern that surveys of galaxies reveal a pattern that resembles a web rather than a fog. On the larger scales, galaxies do not spread evenly. They gather into clusters, line up along filaments, and form sheet-like walls that outline wide regions where galaxies are scarce. Those wide regions are called cosmic voids. A void is not a hole cut out of space. It is a volume where the density of matter is well below the cosmic mean. Matter here includes the ordinary matter made of atoms and the dark matter that dominates mass and shapes the gravitational landscape. Over billions of years, gravity causes matter to stream from under-dense regions toward denser ones. This flow sharpens filaments and leaves void interiors more evacuated relative to the mean. The Boötes Void becomes a prominent example because early redshift surveys show a striking deficit of bright galaxies across a very large region in the direction of the constellation Boötes at a specific range of distances. The name ties it to a part of the sky, but the void itself is three-dimensional. It is defined by a direction and a distance range, not by the foreground stars that form the constellation. The scale is the first thing to hold steady. The Boötes Void spans a region so large that light takes hundreds of millions of years to cross it. In a typical region of similar size and distance, a survey above a given brightness threshold would record many galaxies. In the Boötes Void, far fewer are recorded. That is the core observational statement. Yet it is not the same as saying nothing is there. Under the same cosmic rules, void interiors still contain dark matter structure, thin gas, and a sparse population of galaxies that may be faint, small, or diffuse. The word void is therefore a shorthand for a low-density environment, not a promise of emptiness. The project title says there is an object in the Boötes Void that should not exist. Before that phrase can have a clear meaning, the setting must be made precise. In astronomy, an object can mean many things. It can mean a galaxy, a group of galaxies, a quasar powered by a central black hole, a cloud of gas seen in absorption, a diffuse glow, or even a statistical feature inferred from many measurements. Each of these carries different implications. An object that should not exist usually implies that the inferred object would require physical conditions or probabilities that are not expected in a void interior. But expectations can be simplified and wrong. They can also be shaped by the limits of surveys that first defined the void. Therefore, the first discipline is to treat the void as a measured underdensity, and to separate the idea of underdensity from the idea of prohibition. A void is a region where certain kinds of structures are rarer, especially massive clusters and rich groups, because those require deep gravitational wells that are less common in low-density regions. But rare is not never. A large volume can contain outliers. In addition, voids are often mapped using bright galaxies as tracers. Bright galaxies prefer dense environments, so voids defined by bright galaxies can appear more empty than the mass distribution truly is. This tracer bias means that an object that seems to contradict a bright galaxy void map may simply be a kind of object that the map is not sensitive to. For example, a low surface brightness galaxy can be present and remain undetected in a shallow optical survey. A gas-rich galaxy can be more easily found in radio surveys than in optical. A small group can exist even if it contains no very bright member. Therefore, an object that should not exist may instead be an object that was not counted. The Boötes Void also has boundaries that are not sharp. It is not a perfect sphere with a clean edge. It is a transition in density. Different void-finding methods draw different outlines based on chosen thresholds and smoothing scales. One method may define the void interior as the largest region below a density cut. Another may define it by connecting empty spheres. Another may use a watershed algorithm on a reconstructed density field. These approaches generally agree on the presence of a large underdense region in this direction, but they can differ on the precise boundary. This matters because an object near the boundary can be described as inside the void, under one definition and outside under another. Therefore, when an object is said to be in the Boötes Void, the phrase must include a distance placement and a boundary definition. Without a secure distance, a source seen in the void direction could be in front of the void within it, or behind it. The line of sight continues beyond the void and the background universe is rich. Many dramatic objects such as distant active galaxies can lie behind the void and appear projected onto it. If their distance is misestimated, they can be mistakenly placed in the void and appear impossible. Secure redshift measurement is therefore central. The outer setting also includes the background fields that fill space. The cosmic microwave background is present everywhere. The ultraviolet background produced by galaxies and quasars across the universe also fills intergalactic space and keeps much of the diffuse gas ionized. Inside a void, the local contribution from nearby galaxies is reduced, but the global background remains. This influences the ionization state of gas and the detectability of absorption lines. It also influences the lifetimes of energetic particles because relativistic electrons lose energy by scattering cosmic microwave background photons. These influences are subtle but important when interpreting faint signals in low-density regions. The Boötes Void is also part of a dynamical flow. Matter moves. Over long times, void interiors tend to expand in the sense that their underdensity becomes more pronounced relative to the mean and matter streams toward surrounding filaments and walls. Within the void, there can still be faint filaments and small halos. These can host small galaxies and guide gas flows. Therefore, the interior can contain structure even while remaining underdense. This is one reason that a single object inside a void is not by itself a paradox. The paradox would require that the object's properties imply a deep gravitational well or a dense environment inconsistent with the measured underdensity and with the absence of supporting mass traces. In calm terms, the outermost framing is this. The Boötes Void is a large underdense volume within the cosmic web defined statistically by a deficit of bright galaxies over a substantial distance range. It is not empty, and its boundary is a gradient. Objects can exist within it. Especially faint galaxies and thin gas and rare energetic systems can occur because the volume is large. The phrase should not exist becomes meaningful only when the object category is specified and when the object is placed securely in 3 dimensions relative to the void's interior. With this broad framing steady, the next inward step is to describe how the void is identified and mapped in practice, because that mapping determines what counts as inside, and it determines which kinds of objects can be missed, creating the appearance of contradiction. The Boötes Void is identified through a procedure that turns a sky full of points and smudges into a 3-dimensional distribution. It begins with a galaxy survey. A survey measures positions on the sky and brightness in one or more bands. Brightness alone does not reveal a void. A void is a statement about density and volume. Therefore, distance is required. Distance at these scales is inferred mainly through redshift. When a galaxy spectrum is obtained, known spectral features are shifted to longer wavelengths because space expands. That shift is measured and expressed as redshift. Under a standard cosmological model, redshift relates to distance and to look-back time. With enough galaxies placed in this way, one can reconstruct the large-scale distribution and measure density variations. The Boötes Void appears as a region in that reconstructed volume where the density of galaxies falls far below the mean over a large connected volume. The first inward clarification is that a void is defined relative to traces. Galaxies trace mass, but not perfectly. Bright galaxies are biased traces because they form preferentially in denser regions, and their detectability depends on luminosity and surface brightness. A region empty of bright galaxies can still contain substantial mass and many faint galaxies. Therefore, the appearance of a void depends on the tracer sample. Early surveys that bring the Boötes Void into focus often rely on relatively bright galaxies, because those were the easiest to obtain spectra for at the time. Later surveys with deeper imaging and more spectra reveal more faint galaxies and refine the density field. The void remains underdense, but its exact boundaries and its apparent emptiness can change. This means that any statement about an object that should not exist must specify what the void is defined by. If the void is defined by the absence of bright galaxies, then a faint galaxy inside it is not a contradiction. It is a reminder that the definition is tracer-specific. Survey selection functions are another essential inward detail. No survey sees all galaxies. There is a limiting magnitude, meaning a faintest detectable brightness. At larger distances, only the most luminous galaxies are visible above that limit. At smaller distances, fainter galaxies are visible. Therefore, the sampled galaxy population changes with distance. If one simply counts galaxies without correcting, for this density estimates can be biased. To address this, analyses often construct volume-limited samples. A volume-limited sample includes only galaxies brighter than a chosen absolute luminosity threshold that would be detectable across the entire distance range of interest. This allows fair comparison of densities. The trade-off is that it removes faint galaxies from the analysis even when they are detected because the threshold is chosen for completeness. Therefore, a void defined with a volume-limited bright galaxy sample is deliberately blind to many faint galaxies. That blindness is useful for consistent mapping, but it can create the impression of emptiness. When later observers find faint galaxies in the same volume, the find is real, but not inconsistent with the original void definition. Another inward detail is how void boundaries are drawn. Because galaxy distributions are discrete, a void is not identified by drawing a line around a sharp edge. It is identified by algorithms that operate on a point set or on a reconstructed density field. Some methods search for the largest empty spheres that can be placed in the galaxy distribution. Empty means containing no galaxies above the chosen threshold. By tiling these spheres and connecting overlapping ones, the algorithm defines a void region. This approach is intuitive, but it approximates shapes with spheres and can miss irregularities. Other methods smooth the galaxy distribution into a continuous density field using a kernel, then mark all regions below a density threshold and connect them. This captures more complex shapes, but depends on the chosen smoothing length. A third family of methods uses a watershed approach, treating the density field like a topographic landscape and identifying basins as voids. This can produce void networks and complex boundaries. Each method can identify a Boötes underdensity, but the precise boundary differs. Therefore, a claim that an object lies inside the void should ideally be tested against multiple definitions. If the object lies deep within the interior under all of them, the placement is robust. If it lies near the edge under some definitions, the placement is less robust, and the sense of impossibility should be reduced. Distance uncertainty interacts with boundaries. Spectroscopic redshifts are relatively precise, but they still include peculiar velocities, the motions of galaxies relative to the Hubble expansion. In void regions, peculiar velocities tend to be coherent outflows from the interior toward the walls, but individual galaxies can have motions that shift their redshift slightly. This effect can move galaxies across a boundary in redshift space maps, especially near the threshold. Photometric redshifts have larger uncertainties and can scatter objects across boundaries more readily. Therefore, the reliability of distance placement is a direct inward constraint on the claim. If the object's distance is not securely measured, the claim that it is inside the void remains uncertain. Survey geometry also matters. Surveys have footprints, and they have masked regions where data is missing or unreliable. If a void overlaps a survey edge or a heavily masked region, the density estimate can be biased low because galaxies are missing. Modern analyses correct for this with masks and boundary-aware algorithms, but residual issues can remain. The Boötes Void is large enough that it appears in multiple surveys, which supports its physical reality. Yet local boundary details can still be sensitive to survey completeness. Therefore, the inward approach to mapping includes checks that the void is not an artifact of missing data, and that the object is not located in a region of poor coverage. Another mapping issue is the difference between galaxy number density and mass density. Voids are often defined by galaxy counts, yet galaxy formation efficiency varies with environment and with halo mass. A region can have low galaxy counts, but not as low mass density as the counts suggest. This difference is called bias. In void interiors, bias can be significant because luminous galaxies are rare. Therefore, a mass tracer like weak lensing might show a less extreme underdensity than the luminous galaxy map. This again reduces the sense of impossibility for certain kinds of objects. If the claim is that a massive object exists inside the void, the inward check is whether mass tracers support a local enhancement. If they do, then the void definition may be too reliant on luminous tracers. If they do not, then the distance or nature of the object should be reconsidered. A final mapping concern is the three-dimensional geometry of the void. A void can have internal ridges and pockets of higher density. It can contain small groups and faint filaments. These may not show up in bright galaxy maps, but they can exist. Therefore, mapping does not end with drawing a boundary. It includes describing internal structure at the depth allowed by data. This internal structure can host objects that appear isolated in coarse maps, but are not isolated in reality. In calm terms, the identification and mapping of the Boötes Void is a careful statistical reconstruction from galaxy survey data constrained by selection limits, tracer bias, boundary algorithms, and distance uncertainties. An object that should not exist inside the void can only be assessed against this mapping framework. The next inward step is to define what is meant by an object in the claim, because without specifying whether the object is a galaxy, a group, a diffuse structure, or an inferred mass feature, the claim remains a shape of words rather than a testable statement. The phrase "an object in the Boötes Void" can point to very different physical realities, and each reality carries a different set of expectations for a void interior. An object can be a luminous galaxy visible in optical light. It can be a low surface brightness galaxy that spreads its light thinly and is hard to detect. It can be a gas-rich galaxy found through neutral hydrogen emission. It can be a quasar or other active galactic nucleus powered by accretion onto a supermassive black hole. It can be a small group of galaxies bound by gravity. It can be a diffuse structure such as a radio lobe, a filament of warm gas inferred from absorption, or an extended region of emission. It can also be an inferred mass concentration detected statistically through weak gravitational lensing. The inward task is to name the object category, because the idea that it should not exist usually comes from applying the wrong expectation to the wrong category. A galaxy in a void is not forbidden. A rich cluster deep in a void interior would be rare. A diffuse emission feature might be more likely to be foreground or background if distance is uncertain. Each category sets its own constraints. A luminous optical galaxy is the simplest category. If such a galaxy is placed securely at the void distance, it implies that at least one luminous system exists in an underdense region. This is not impossible. Voids contain galaxies. The more relevant question is whether the galaxy's properties are typical of void galaxies or unusual. Void galaxies are often thought to be smaller and less evolved, but this is a tendency, not a law. Some void galaxies can be substantial disks with ongoing star formation, especially if they have retained gas and avoided disruptive interactions. Therefore, a luminous galaxy can exist in a void interior. Its presence may simply indicate that galaxy formation proceeds even in underdense regions, albeit at lower frequency. A low surface brightness galaxy is another category that can produce apparent contradiction. Such galaxies can be physically large but faint per unit area, making them difficult to detect in standard surveys. A region mapped as empty of bright galaxies could contain low surface brightness galaxies that were missed. Deep imaging can reveal them. If such a galaxy is found in the void interior, it can seem like an object where nothing should be, but in fact it is consistent with the idea that void mapping by bright galaxies is incomplete. The claim then shifts from impossibility to survey sensitivity. A gas-rich galaxy detected through neutral hydrogen emission can produce a similar effect. Neutral hydrogen surveys can detect galaxies with substantial gas even when starlight is faint. In a void environment, galaxies can retain gas because there is less external stripping. Star formation can be inefficient, leaving large gas reservoirs. Therefore, a void can host gas-rich galaxies. Finding them can feel surprising if the void was defined by optical surveys alone. Again, the contradiction is between traces, not between physics and reality. An active galactic nucleus is another object category that can sound impossible in a void, because active nuclei are often associated with dense environments or with galaxy interactions. Yet active nuclei can be triggered by internal processes and by minor interactions, and they can occur in isolated galaxies. The probability is lower in voids because galaxies are fewer, but the volume can still host some. If a quasar is found in the void direction, the first question is distance. Many quasars are far beyond the void. If a quasar is actually at the void distance, it implies a host galaxy with a feeding black hole. This is not forbidden. It is rare and therefore noticeable. Its jets can create large radio structures. In low-density environments, radio lobes can expand more freely. Therefore, a void interior active galaxy could produce an extended radio signal that seems large and out of place. The plausibility depends on finding the host and confirming the redshift. A galaxy group is another category. Voids have fewer groups, but small groups can exist, especially along faint internal filaments. If a group is found in the interior, it might indicate that the interior contains substructure. It might also indicate that the object is not deep interior, but near a boundary ridge. The group's mass and richness are the key. A small group of a few faint galaxies is plausible. A rich cluster is less plausible. Therefore, when a claim says an object should not exist, one should ask whether the object is being described as a massive cluster-like system or as a small association. The vocabulary often blurs this. A handful of galaxies can be called a cluster in casual language, but physically it may be a modest group. The meaning changes the level of surprise. Diffuse structures are a category where distance ambiguity is common. A diffuse radio feature could be a relic lobe system from an active galaxy, which could be inside or behind the void. A diffuse optical glow could be galactic cirrus. A diffuse X-ray emission could be background cluster gas. A diffuse absorption signature could be void gas or galaxy halo gas. Therefore, for diffuse objects, the category includes not only the physical phenomenon, but also the method of distance anchoring. Without a spectral line redshift or a clear association with a host at known redshift, a diffuse feature cannot be confidently placed within the void. This is why diffuse object claims require more caution. The same is true for weak lensing inferred objects. A lensing signal can suggest a mass concentration, but lensing integrates mass along the line of sight. Assigning it to the void interior requires redshift information for both lenses and sources and careful modelling. Therefore, a lensing detected object in the void direction is not automatically a void interior object. It is a mass feature along the line of sight that may overlap the void distance. The inward progression also requires attention to language. The phrase should not exist often contains an implicit model. The implicit model might be that void interiors are empty. Another implicit model might be that galaxy formation is suppressed completely in such regions. Another might be that certain signals require dense environments. The category analysis replaces these implicit models with explicit ones. For a galaxy, the model is galaxy formation in low-density halos. For a group, it is the distribution of halos and the probability of associations. For an active nucleus, it is feeding and duty cycles in isolated galaxies. For diffuse emission, it is density dependence of emissivity and the presence of acceleration sites. Each model yields an expectation of rarity and signal strength, not a simple yes or no. In calm terms, an object in the Boötes Void can mean a range of things. Most of these are not forbidden. Some are simply hard to detect. Some are likely to be misassigned in distance if care is not taken. Therefore, before moving further inward into interpretation, the next step is to trace how a claimed object signal reaches the observer through foreground and background layers, because misplacement along the line of sight is the most common reason an object seems to be in the void when it is not. That path analysis sets the stage for deciding whether the object truly belongs to the void interior or only to its direction on the sky. An object assigned to the Boötes Void must be separated from the many other things that lie along the same direction. The line of sight toward Boötes is a long corridor through space. It passes through the Milky Way, through nearby intergalactic space, through the void's distance range, and then onward to far more distant structures. Light radio waves and high-energy photons travel through this corridor and collect the imprint of what they pass. Instruments then add their own imprint. At this inward stage, the goal is to distinguish origin from path. A genuine void interior object must be anchored in distance and must survive tests against foregrounds, backgrounds, and measurement artifacts. The first foreground layer is the Earth environment for ground-based observations. The atmosphere absorbs some wavelengths and emits in others. In optical bands, atmospheric turbulence blurs images, spreading light and reducing the ability to detect low surface brightness features. In infrared, atmospheric emission creates a bright background. These effects are corrected through calibration and processing, but residual errors remain. Space-based observations avoid atmospheric effects, yet they still face instrumental backgrounds and scattered light. Therefore, even before considering the sky, one must consider whether the signal sits near the limits, where small calibration errors can create large apparent structures. This is especially relevant for claims based on faint, diffuse emission. The second foreground layer is the Milky Way. Dust in the Milky Way absorbs and scatters starlight. It also emits strongly in the infrared. Fine dust structures called cirrus can create faint filaments and patches across the sky. In deep optical imaging, dust scattering can produce diffuse galactic light, a faint glow that follows dust structure. These foreground features can mimic extended extragalactic light. In radio, the Milky Way produces synchrotron emission that varies across the sky and can dominate large angular scales. It also produces line emission from neutral hydrogen and molecules. In X-rays, hot gas in and around the Milky Way produces diffuse emission. Therefore, a signal seen in the direction of a void can be galactic, even if it looks like a large faint structure. For an object claim, the inward checks include comparing with dust maps, checking for correlation with infrared cirrus, and testing spectral behavior against known galactic emission. If a feature aligns with dust structure and has colors consistent with scattered starlight, it is likely foreground. If it does not, the case for extragalactic origin strengthens. Another layer is nearby extragalactic structures. A source could be in the foreground closer than the void. A faint galaxy halo or a nearby group can project into the void direction. Without redshift, it can be misassigned. Spectroscopic redshift resolves this for compact sources, but for diffuse emission it can remain ambiguous. Neutral hydrogen line emission is an exception because the emission frequency provides redshift. Therefore, a neutral hydrogen detection can be placed in distance directly. For continuum signals association with a host galaxy at known redshift is essential. The corridor also contains absorption features. Gas in the Milky Way and in intervening intergalactic structures can absorb portions of a spectrum. This can alter the colours of background sources and lead to photometric redshift errors. Dust reddening can have a similar effect. Therefore, an object placed at the void distance based on photometric information alone can be misassigned if foreground effects are not fully accounted for. This is a quiet but common pathway to apparent anomalies. The background layer is rich. Beyond the void, the universe continues with filaments, clusters, and active galaxies. The Boötes Void occupies only a finite distance interval. Many objects behind it can appear in the same patch of sky. In fact, because the void has fewer nearby galaxies, background objects may stand out more clearly in projection. A distant quasar behind the void can be bright and can look isolated against a sparse foreground. If its distance is not measured, it might be described as inside the void. This misplacement can make the object seem impossible, because quasars are not expected to be common at the void distance. The inward check is therefore redshift. A spectrum can tell whether a quasar is far beyond. Similarly, a background cluster can produce extended X-ray emission and can be projected onto the void. If distance is misassigned, a background cluster can be mistaken for a void interior hot gas structure, which would indeed be surprising. Here again, redshift of cluster galaxies or spectral features in the X-ray emission are needed to anchor distance. Gravitational lensing is another path effect. Lensing can magnify background objects and can distort shapes. A background galaxy behind the void could be magnified, making it appear brighter than expected for its redshift or leading to misclassification. Lensing also integrates mass along the line of sight, so a lensing inferred mass feature in the void direction could be dominated by structures at other distances. Assigning it to the void interior requires careful redshift modelling. Therefore, lensing can both alter appearance and complicate distance assignment. Confusion is a path-related measurement limit. Many faint sources lie below the detection threshold and below the resolution limit. Their combined light can produce a smooth background or a mottled texture. In infrared and radio surveys, confusion noise can limit sensitivity. A region with apparent diffuse emission can be a blend of unresolved background galaxies rather than a true diffuse structure. This is particularly relevant in void directions because the background universe is not underdense even if the void interval is. Therefore, a diffuse glow in the void direction can be dominated by background sources behind the void. Statistical tests and higher resolution observations can help disentangle this. Instrumental artifacts are the final imprint. In optical imaging, scattered light and imperfect sky subtraction can create large-scale gradients and rings. In radio interferometry, calibration errors and incomplete sampling can create spurious extended structures and side lobes around bright sources. In X-ray imaging, particle backgrounds and detector variations can create patterns that resemble faint diffuse emission. These artifacts can be convincing. Robustness tests include checking whether the feature appears in independent datasets, whether it persists under different processing pipelines, and whether it has properties expected of real astrophysical emission, such as consistent spectral behavior. The inward lesson is that the path from the object to the detector can create false objects. Therefore, the claim that an object is inside the void must be supported by distance anchoring, and by multi-wavelength and multi-instrument checks that exclude foregrounds, backgrounds, confusion and artifacts. Only after the origin is stabilized can the discussion move to baseline physical conditions inside the void and to whether the object's properties are consistent with that environment. With the path clarified, the next inward step is to establish those baseline conditions, the typical density gas state radiation environment, and interaction rates expected in a large void, because those baseline conditions define what kinds of objects are common, what kinds are rare, and what kinds would indeed be unusual if confirmed deep inside. Baseline physical conditions inside the Boötes void can be described as a quiet set of averages with local exceptions. The void is defined by low density relative to the cosmic mean. That low density changes how gravity assembles structures, how gas behaves, how radiation shapes ionization, and how often galaxies interact. None of these changes turn processes off. They change rates and typical scales. Therefore, when an object is said to be one that should not exist in the void, the question becomes whether the object requires conditions that are incompatible with these baseline tendencies, or whether it simply sits on the rare end of what the baseline allows. The first baseline element is the distribution of dark matter. Dark matter forms halos and filaments, and in a void the average dark matter density is below average. This makes deep gravitational wells rarer. Massive clusters and rich groups are less likely to form in the deepest interior. Small halos are still expected. Many of those halos may be too low mass to form luminous galaxies efficiently. Therefore, the void can contain dark matter structure that is not strongly traced by bright galaxies. If an object claim involves mass, the baseline expectation is that large mass concentrations are rare but not forbidden, while numerous low-mass halos are common. A second baseline element is the state of diffuse gas. Most of the space inside the void is filled with thin intergalactic gas composed mainly of hydrogen and helium. In the present universe, this gas is mostly ionized by the ultraviolet background. The gas density is low, so the rate of collisions is low, which makes emission weak. This is why void interiors are hard to see in emission. Yet the gas can still be detected in absorption, because absorption depends on the number of atoms or ions along a line of sight, rather than on collisions. The baseline expectation is therefore that absorption systems at the void distance are plausible, while bright emission from void volume filling gas is unlikely. Temperature is a related baseline. Photoionized diffuse gas often sits at temperatures that correspond to particle motions typical of tens of thousands of degrees. Shocks and feedback can create hotter pockets, but widespread high-temperature gas at densities sufficient for strong X-ray emission is not expected in the deepest interior. Therefore, an extended X-ray bright halo placed securely deep inside the void would be unusual and would require careful confirmation of both distance and mass. A third baseline element is the radiation environment. The cosmic microwave background is everywhere. The ultraviolet background is also pervasive. Inside a void, the local radiation from nearby galaxies is reduced because there are fewer nearby galaxies. This can slightly alter ionization states and heating, but it does not remove ionizing radiation entirely. Therefore, void gas is still generally ionized. The cosmic microwave background also influences the lifetimes of relativistic electrons through inverse Compton scattering. This creates a baseline constraint for radio emission. Energetic electrons cool over time regardless of the local gas density. Therefore, sustained radio synchrotron signals require either recent injection, ongoing acceleration, or conditions that keep emission detectable at the observed frequencies. A fourth baseline element is interaction rate. In void interiors, galaxies are farther apart, so close encounters and mergers are less frequent. This affects galaxy evolution. Without frequent interactions, galaxies can evolve more quietly. They can retain gas longer because they are less likely to be stripped by hot, intra-cluster gas, which is largely absent. They can maintain extended disks with fewer tidal disturbances. Star formation can proceed at low levels over long times rather than being strongly triggered by interactions. Therefore, void galaxies are often expected to be gas-rich and moderately star-forming or to have low star formation efficiency. This baseline supports the plausibility of finding faint gas-rich, low-surface brightness galaxies inside voids. Their discovery can seem contradictory only if the void is imagined as empty rather than as underdense. A fifth baseline element is the presence of substructure. Even in an underdense region, the density field has variation. Voids contain internal ridges and faint filaments in dark matter and gas. These features can guide gas flows and host small halos. They can also host the rare small group. Therefore, a modest association of faint galaxies inside the void interior can be a sign of internal substructure rather than a violation of the void concept. The baseline expectation is not that the interior is smooth, but that its structures are fewer, smaller, and lower contrast. A sixth baseline element is detectability. Voids are defined and perceived through surveys, and surveys have biases. Bright galaxies are easy to see, and are used to map voids, but they leave out many faint systems. Low surface brightness objects are missed more often than compact ones. In radio, certain surveys reveal gas-rich systems that optical surveys miss. Therefore, baseline expectations are conditioned by the observing method. A claim that an object should not exist can arise simply because the observer's mental baseline is built from one tracer. When another tracer is used, the object appears. In that case, the surprise is a shift in perspective rather than a conflict with physical baselines. Within these baselines, different object categories have different degrees of expected rarity. A single faint galaxy is expected. A handful of faint galaxies can occur. A luminous galaxy can occur, though less commonly than in filaments. An active nucleus can occur because black hole accretion is not exclusive to dense environments, but it is less frequent. A large radio lobe system can occur if an active galaxy is present, and if the lobe is young enough or supported by ongoing activity. A volume-filling hot gas structure is less expected because it requires density and heating. A rich cluster is unlikely deep inside because it requires a large mass concentration and a surrounding environment that supports its assembly, though it is not impossible in principle, if the void definition is based on luminous tracers and if the mass distribution is more complex. Therefore, the baseline conditions do not deliver a single verdict. They provide a map of plausibilities. They indicate where the word should not exist might be justified in a narrow technical sense, and where it is a sign of a simplified baseline. The inward task now is to inventory what material remains inside a void and how it is traced, because the claim about an object often confuses visible traces with the underlying material. Dark matter, ionized gas, neutral gas stars, dust and energetic particles each have different expected distributions and detection modes in a void interior. Identifying which component is being detected is the next inward step toward turning the claim into a testable statement. What remains inside a void depends on the distinction between mass and light. In the Boötes Void interior, mass is still dominated by dark matter. Light is still produced by stars and by gas in certain conditions. The void is underdense in each component compared with the cosmic mean, but none of the components vanishes. The inward step here is to inventory the main materials and to connect each to the way it is observed, because an object that should not exist is often an object that belongs to a component the original void map did not trace well. Dark matter is the first component because it carries most of the mass. It does not emit light, so it is observed indirectly. One method is gravitational lensing, where foreground mass distorts the apparent shapes of background galaxies. Another method is the dynamics of galaxies, where their motions respond to gravitational potentials. In void interiors, the dark matter density is lower, and the most massive halos are rarer, but small halos still exist. Many of those halos may host faint galaxies or no galaxies at all. Therefore, a gravitational signal of mass substructure inside the void is not forbidden. The question is scale. A cluster scale mass concentration would be rare while a population of small halos is expected. Because lensing integrates mass along the line of sight, any mass inference must also be tested for distance association. Yet the presence of dark matter structure inside the void is a baseline expectation. Ordinary gas is the second component and fills most of the volume. In void interiors, the gas is predominantly hydrogen and helium, and is mostly ionized. Ionized gas in low-density conditions emits little, because emission depends on collisions and collisions depend on density. Therefore the gas is not easily seen in emission. It is more easily seen in absorption against background sources. Hydrogen can produce absorption lines that reveal neutral fractions, and metals can produce absorption that reveals enrichment and temperature. Absorption is sensitive to thin gas because it depends on column density. A long path through low-density gas can still yield a detectable column. Therefore, absorption detections inside a void distance range are consistent with the presence of diffuse gas. They are not contradictions. Neutral gas is another state of the ordinary gas. Neutral hydrogen is uncommon in diffuse void intergalactic space because the ultraviolet background ionizes it. Neutral hydrogen persists mainly in denser regions, where gas can shield itself, especially in galaxies and their immediate surroundings. Neutral hydrogen can be observed through its characteristic radio line emission, which provides redshift and therefore distance. This makes neutral hydrogen surveys an important tracer of void galaxies. A region mapped as empty by optical bright galaxy surveys can contain neutral hydrogen-rich galaxies that are faint in optical light. Finding them can feel like finding an object where nothing should be. In reality, it reveals that the void was mapped with a tracer that is not sensitive to that population. Stars are the next component and are confined to galaxies. In void interiors, galaxies exist but are less numerous. The galaxies can be low mass and faint, and they can also be diffuse. Low surface brightness galaxies can have substantial stellar mass, but spread over a large area, making them difficult to detect in standard imaging. In deep imaging, they can appear as ghostly extended disks. Their existence is plausible in void environments because interactions are rare and disks can remain undisturbed, and because star formation can be spread out at low intensity. Therefore, a stellar object inside the void can be a galaxy that was previously missed due to surface brightness limitations. Dust is a minor mass component, but important for its effects on light. Dust is created in stars and spreads through galaxies and their halos. In void interiors, overall dust content is lower on average because there are fewer galaxies, but local dust around galaxies can still exist. Dust absorbs and scatters light-altering colours and brightness. Dust also emits in infrared. In observational terms, dust in the Milky Way is a major foreground that can mimic faint extragalactic structures. Therefore, dust is both a physical component of galaxies and a confounding factor for detecting faint objects in void directions. An object claim based on diffuse optical light must therefore consider whether the light is scattered by galactic dust rather than emitted by void galaxies. Energetic particles are another component. Cosmic rays, especially relativistic electrons, can produce radiosynchrotron emission when magnetic fields are present. In void interiors, the density of acceleration sites is lower because galaxies and strong shocks are rarer. Magnetic fields in void intergalactic space are not well measured, but some field may exist due to early seeding and due to outflows from galaxies. Therefore, energetic particle-related signals are possible, but expected to be faint and rare. A radio signal inside the void can be produced by a rare active galaxy, with jets by supernovae and star formation in a galaxy, or by particle acceleration at shocks and faint filaments. The plausibility depends on whether the signal can be associated with a source at the void distance and whether its spectrum and morphology match known mechanisms. Another component is the background radiation fields that interact with matter. The ultraviolet background maintains ionization in diffuse gas. The cosmic microwave background acts as a sink for electron energy through inverse Compton scattering. These fields influence what can persist. For example, old radio-emitting electron populations fade because of energy losses to the cosmic microwave background. Therefore, any extended radio structure in a void must satisfy microphysical lifetime constraints. This is a component in the sense that it sets the environment for energetic processes. Bringing these materials together, a void interior is underdense but not empty. Dark matter structure exists diffuse. Ionized gas fills much of the space. Neutral gas persists in galaxies. Stars exist in a sparse galaxy population. Dust exists locally around galaxies, and as a galactic foreground, and energetic particles and magnetic fields can appear through rare energetic events. Therefore, an object that should not exist is often a mismatch between what is expected of a bright galaxy-mapped void and what is actually present in mass and faint traces. The inward progression now turns to a practical complication. Dust foreground structures and measurement limits can create illusions at the faint edge. Because many void object claims involve very faint light or diffuse emission, the next inward step is to describe how dust and foreground patterns can mimic objects, and how observers distinguish true void interior structures from foreground and background artifacts. The boundary between a true faint object and a convincing illusion is often drawn at the level of dust unresolved backgrounds and the behavior of instruments near their limits. In the Boötes Void direction, the sky may look less crowded with nearby bright galaxies, but it is not empty of foreground structure or of distant background sources. When claims arise that an object should not exist in a void, they often arise because the detection is near a threshold where small effects can produce large apparent features. The inward task at this stage is to treat dust and faint glows as physical and observational realities that must be separated before an object can be declared real and placed in distance. Milky Way dust is the most persistent foreground. Dust grains in the interstellar medium absorb and scatter starlight. Absorption dims background sources and reddens them. Scattering produces diffuse galactic light, a faint glow that follows dust structure and the distribution of bright stars. Dust also emits thermally in the infrared, producing cirrus emission that can be bright and structured on wide angular scales. In deep optical imaging, diffuse galactic light can appear as wispy filaments and patches that resemble low surface brightness, extragalactic features. In infrared maps, cirrus can resemble extended halos. Therefore, any claim of a diffuse optical or infrared object in a void direction must check for correlation with dust maps. If the feature aligns with dust structure, and if its color resembles scattered starlight, it is likely galactic. If it does not align, and if it has a coherent galaxy-like profile, the extragalactic case strengthens. The difficulty is that both kinds of features can be faint and extended, and at the deepest limits separating them can require multi-wavelength data. Another dust-related effect is reddening of compact sources. A background galaxy behind the void can have its colors altered by foreground dust. Photometric redshift estimates rely on colors, so dust reddening can shift inferred distances. If a distant galaxy is reddened, it might be misclassified as nearer and be placed at the void distance. The result is an object that appears too luminous or too massive for a void galaxy. This can be corrected by applying dust extinction maps and by using spectroscopy where possible, but residual uncertainties can remain, especially for faint sources. Therefore, a calm test for a surprising void object is whether its distance is based on spectroscopy or on photometry, and whether dust correction is robust. Unresolved background sources are another source of false objects. The universe behind the void contains many faint galaxies and active nuclei. Even if the void interval itself has fewer galaxies, the line of sight continues beyond it. In imaging surveys, many of these background sources are below the detection threshold, or are unresolved, and their combined light forms a background glow. In infrared and radio surveys, confusion noise arises when the density of faint sources is high relative to the instrument resolution. This confusion can produce apparent diffuse emission, especially when point sources are subtracted imperfectly. If an extended faint patch remains, it can be tempting to treat it as a diffuse structure in the void. The inward check is to estimate the expected confusion contribution and to test whether the residual has the statistical properties of an unresolved source field. Higher resolution observations can break confusion by resolving sources. Multi-frequency analysis can also help because a population of background galaxies has a different spectral behavior than true diffuse synchrotron emission. In radiogalactic synchrotron emission is a dominant foreground. It varies across the sky and can produce large-scale features. Because it is emitted by relativistic electrons in the Milky Way's magnetic field, its spectrum typically follows a power law over certain frequency ranges, and it can show polarization. Distinguishing galactic synchrotron from extragalactic diffuse emission requires careful modelling, including the use of multiple frequencies and the examination of spatial correlations with known galactic structures. This is difficult because instrumental calibration and imaging choices can imprint patterns. In radio interferometry, incomplete sampling of spatial frequencies can create artifacts that resemble diffuse emission, especially on large angular scales. Therefore, claims of diffuse radio objects in void directions must demonstrate that the feature is not a calibration artifact and that it persists across independent surveys and instruments. Instrumental behavior is a major source of illusion in deep optical imaging. At very low surface brightness, sky subtraction becomes the dominant step. The night sky has its own brightness, and scattered light inside the telescope can create gradients and reflections. Flat fielding, which corrects sensitivity variations across the detector, must be extremely accurate. Small errors can create false structures. For example, an imperfect background model can leave a faint ring around a bright star. Scattered light can create ghostly arcs. In mosaic surveys that stitch multiple exposures together, small differences in background can create seams and gradients. These effects can be mistaken for real diffuse objects. The inward check is to test the feature under different processing pipelines to confirm it in independent datasets and to ensure it does not align with known instrumental patterns. In X-ray observations, particle backgrounds and detector variations can create apparent extended emission. Faint cluster-like glow can be mimicked by background fluctuations and point sources can blend. Therefore, X-ray claims require careful background modelling and point source removal, as well as checks with independent instruments. Absorption studies are also vulnerable to subtle errors. Continuum fitting. The estimation of the intrinsic spectrum of the background source can influence the inferred strength of absorption. Noise spikes can mimic weak lines. Therefore, absorption detections require significance tests, and ideally confirmation through multiple lines of the same system. Yet absorption also offers a way to avoid some illusions, because lines have specific wavelengths and patterns. A real absorption system often appears in multiple transitions at consistent redshift. This pattern makes it harder to confuse with a random noise. Therefore, absorption can be a robust probe of void gas, though it still samples only narrow sightlines. A separate class of illusion arises from the way the mind interprets maps. When a region is labelled a void, any object projected onto it can appear more striking. The same object in a crowded field might feel ordinary. This is a psychological overlay rather than a physical one, but it influences language. The inward discipline counters this by returning to distance and to quantitative comparisons. How many such objects would be expected in the surveyed volume? How often do such objects appear in similar environments? Is the object's location truly deep interior? These checks reduce the weight of impression. In calm terms, dust and faint glows are not merely contaminants, they are physical components that must be accounted for. Milky Way dust creates structured foreground light and reddening. Background source confusion creates smooth or mottled glow. Radio and X-ray foregrounds add additional structure. Instruments imprint patterns when pushed to faint limits. Therefore, before accepting that an object truly resides in the void, the detection must survive tests against these illusions, ideally through independent data and multi-wavelength consistency. With illusions and foregrounds accounted for, the inward progression can return to genuine physical drivers. If the object is real and at the void distance, what energy sources could produce its observed emission or absorption? Stars, stellar feedback, black hole, accretion, and shocks in faint structure formation are the main candidates. The next inward step is to examine these energy sources in a void environment, because the plausibility of the object depends on whether its brightness spectrum and extent can be produced by known processes under low-density conditions. If an object is real and placed at the Boötes Void distance, its existence must be supported by an energy budget consistent with known processes. Energy sources here mean what powers the observed light radio waves or high-energy emission, or what creates the physical conditions that generate absorption and line signatures. In a void interior, the same engines operate as elsewhere, but their typical frequency per unit volume is lower, because there are fewer galaxies and fewer dense structures. The inward task is to connect object categories to plausible energy sources and to note where certain sources become strained without additional evidence. Starlight is the simplest energy source. A galaxy shines because it contains stars. Young massive stars emit strongly in ultraviolet and can ionize surrounding gas. Older stars emit more in visible and near-infrared. In void galaxies, star formation is often slow and extended because interactions are rare and gas can be retained. This can produce galaxies that are gas-rich and continue forming stars at a modest pace for long periods. It can also produce low-surface brightness disks where light is spread out and difficult to detect. Therefore, an optical or infrared object in the void that resembles a galaxy can be powered by ordinary stars. If it seems surprising, the surprise may be about its brightness or size given its environment, which is then a question of rarity and of survey bias rather than of an unfamiliar energy source. Stellar feedback is a second energy source that shapes gas and can power certain emission. Supernovae and stellar winds inject energy into the surrounding interstellar medium. They create hot bubbles, drive outflows, and can ionize gas in extended regions. In low-mass galaxies, which are common in void interiors, gravitational wells are shallow. This makes it easier for feedback to expel gas. In a low-pressure environment, outflows can expand farther. Over time, outflows can carry metals into the surrounding medium and create enriched gas pockets that can be detected in absorption. Therefore, if an object claim involves metal absorption inside the void, stellar feedback from small galaxies is a plausible energy source for enrichment. If the object claim involves faint emission lines in an extended region around a void, galaxy feedback can also contribute, though emission requires density, and thus is likely to be localized. Black hole accretion is a third energy source that can produce objects that feel out of place in a void. When gas falls into a supermassive black hole at a galaxy's center, a fraction of its energy is released as radiation. This can produce a luminous active nucleus with X-ray and optical signatures. It can also launch jets. Jets inflate radio lobes that can extend far from the host galaxy. In low-density environments, lobes can expand more freely, and their large size can appear dramatic. If an object is described as something that should not exist because it is too energetic or too extended for the void, an active nucleus is a plausible mechanism provided a host galaxy at the correct redshift exists. The inward checks include looking for a compact core measuring optical and X-ray spectra for active nuclear signatures and mapping radiomorphology for jet lobe structure. The plausibility also depends on timescales. Relativistic electrons lose energy through synchrotron emission and inverse Compton scattering on the cosmic microwave background. Inverse Compton losses occur everywhere, including in voids. Therefore, a large radio structure must be either relatively young, continuously powered, or experiencing re-acceleration of particles. These microphysical constraints can be tested with radio spectra. Shocks from gravitational flows provide another possible energy source. Even in void interiors, gas moves under gravity. It can stream along faint filaments and into halos. Where flows converge or where gas encounters a change in potential shocks can form. Shocks heat gas and can accelerate particles. In dense regions, such shocks can be strong and produce bright emission. In void interiors, shocks are expected to be weaker and less frequent, but they can still exist along faint internal filaments and around the few halos. If an object claim involves a faint diffuse radio feature without a clear active galaxy host, one hypothesis is synchrotron emission from shock-accelerated electrons in internal filaments, assuming magnetic fields are present. This is challenging because expected emission is faint, and because galactic foregrounds are strong. Therefore, such an object would require exceptional observational care. If confirmed, it would constrain void magnetization and filament structure, but it would not require new laws. Another process is gravitational potential evolution over large scales, which can produce subtle imprints on background radiation, such as small temperature fluctuations in the cosmic microwave background, correlated with large structures. If an object is claimed in a statistical sense, such as a significant anomaly, aligned with the void, the energy source is not a local engine, but the integrated effect of structure along the line of sight. Such claims are sensitive to statistical selection and require careful control of chance alignments. The language of should not exist can be especially misleading here, because it can turn a low significance correlation into a dramatic statement. The inward approach insists on significance tests and on replication in independent datasets. For thermal X-ray emission, the energy source is hot plasma. Hot plasma can be produced by shocks in gravitational collapse and by feedback, yet producing bright extended X-ray emission typically requires gas that is both hot and relatively dense. This is commonly found in galaxy groups and clusters, where gas is confined by a deep gravitational well. In a void interior, such wells are rare. Therefore, if an object claim involves extended X-ray emission in the void, the inward test is whether a mass concentration is present and whether the distance is secure. A background cluster behind the void is a common alternative explanation. If distance anchoring and mass evidence support a void interior hot plasma, the object would be unusual in probability terms, but the energy mechanism would still be known. It would imply a mass structure in an underdense region, and would prompt re-examination of void definition and tracer bias. Background radiation fields also influence what energy signatures persist. The ultraviolet background keeps gas ionized, reducing neutral fractions in diffuse regions. This affects absorption line strengths. The cosmic microwave background limits the lifetime of high-energy electrons through inverse Compton losses. These fields are always present and therefore set baseline constraints. In a void, the absence of strong local radiation fields can mean less local heating and less ionization beyond the global background, which can slightly alter ion ratios. This can influence the interpretation of absorption systems. Therefore, an object whose evidence is chemical or ionic must be interpreted in the context of these fields. At this stage, the energy sources that can plausibly generate objects in a void interior are clear. Stars and steady star formation can power ordinary galaxies, including diffuse ones. Feedback can enrich and shape local gas. Black hole accretion can produce luminous nuclei and extended radio structures. Mild shocks can heat and perhaps accelerate particles in faint filaments. Thermal X-ray emission generally implies dense hot gas and therefore mass confinement. Statistical imprints require careful significance handling. None of these are exotic. The question is which source matches the observed properties and whether the required conditions are plausible given the void environment. The next inward step is to return to boundaries and internal filaments, because many objects that seem to be in the void are actually near the edges or along faint internal ridges where energy sources and material are more available than in the deepest interior. Establishing where within the void the object sits is therefore essential for judging whether it is merely rare or genuinely unexpected. The location of an object relative to the Boötes Void's edges and internal ridges is often the difference between a plausible rarity and a real tension with expectations. A void is not a clean bubble. It is a valley in the density field. Its boundary is a rising slope toward denser walls and filaments. Its interior can contain faint ridges and threads. If an object is said to be in the void, the inward approach asks where in this landscape it sits. An object near the boundary is less surprising, because the boundary is where galaxies and gas structures become more common. An object deep in the interior can be more noteworthy, though still not forbidden depending on the object category. Therefore, the void must be treated as a gradient rather than a binary state. Boundary definitions are the first factor. Different void catalogues and algorithms define different boundaries. A watershed method may include regions that a sphere method would exclude. A density threshold chosen for one tracer sample may shift when a deeper sample is used. Therefore, the same object can be inside the void under one definition and outside under another. The strongest interior association is one that holds across definitions. That requires testing the object's position in 3 dimensions against multiple void reconstructions. It also requires stating the distance uncertainties. A spectroscopic redshift can place a galaxy relatively well. Photometric redshift cannot. Diffuse emission rarely has direct distance anchoring. Therefore, many claims weaken when boundary definition uncertainty is made explicit. An object can still be interesting near a boundary. It simply should not be described as a contradiction of emptiness. The physical boundary region is more than a mathematical surface. It contains denser filaments and sheets where matter accumulates. Gravity draws matter outward from the void interior toward these walls. Gas density rises. The likelihood of shocks increases as flows converge. Galaxies are more common. Therefore, boundary regions are plausible hosts for objects that require more material or more interactions, such as galaxy groups, active galaxies in richer environments, and hot gas. A line of sight can cross such a structure even if the object's projected position appears central on the sky. Because the void is 3-dimensional projection can mislead. A boundary filament can sit at one distance along the line of sight, while the projected coordinates correspond to the void interior. If an object is associated with that filament, it is not a deep interior object even if it appears central in projection. This is why redshift placement is essential. Internal filaments complicate the picture further. Simulations predict that void interiors contain a network of faint filaments and small halos. These filaments have lower density contrast than boundary filaments, but they are real. They can host small galaxies and can guide gas. They can also host mild shocks. A small group of galaxies or a chain of faint galaxies at the void distance can be a visible part of such an internal filament. A set of absorption systems at similar redshifts along nearby sight lines can also hint at an internal filament of gas. Therefore, an object inside the void interior can be associated with internal structure rather than being isolated in a uniform emptiness. This association reduces the sense of impossibility because the object is then part of an allowed substructure. It does not erase the void because the void remains underdense overall. It simply shows that underdense does not mean smooth. Peculiar velocities introduce another boundary-related subtlety. Redshift maps are distorted by galaxy motions relative to the Hubble expansion. In voids, galaxies tend to flow outward, and this can distort the apparent boundary in redshift space. A galaxy physically near the edge can appear shifted inward or outward depending on its velocity along the line of sight. This effect is not as dramatic as the distortions in clusters, but near boundaries it can matter because gradients are steep. Therefore, placing an object relative to the boundary has an uncertainty beyond measurement error. The inward discipline is to acknowledge that uncertainty and to avoid hard claims when the object lies near the threshold. Another boundary complication is tracer bias. If a void is defined using bright galaxies, the boundary may appear sharper and the interior emptier than if defined using fainter galaxies or mass tracers. A region may look like a deep interior based on bright galaxies, but in fact contains several faint galaxies and modest mass structure. In that case, an object that seems to be deep interior is actually in a less extreme environment. This matters especially for claims of improbability. The probability of encountering certain object types depends on the true mass and galaxy density around them, not on the bright galaxy map alone. Therefore, a careful placement of the object uses the deepest available galaxy catalogues, and where possible mass tracers like weak lensing. This placement can convert an impossible narrative into a consistent one. Consider the object categories again under boundary context. A low surface brightness galaxy deep in the void is plausible, and near the boundary it is also plausible. A gas-rich galaxy is plausible anywhere in the void, particularly in quiet interiors where gas retention is easier. An active galaxy is less common in void interiors but can still occur. Near boundaries it becomes more likely. A galaxy group near the boundary is plausible. A rich cluster near the boundary is plausible because boundaries can include walls and filaments that host clusters. A rich cluster deep in the interior is less expected. A diffuse radio lobe system might be associated with an active galaxy. It may be larger in a low-density environment. Its placement relative to boundaries affects whether surrounding material could confine or shape it. A diffuse X-ray emission feature near the boundary might be a group or cluster. In the interior, it would demand stronger evidence and mass support. Therefore, boundary context becomes a filter for plausibility. Importantly, placing an object relative to boundaries is not merely a geometric exercise. It is also an observational one. The void boundary is itself inferred from the distribution of detected galaxies. If an object is found, it may prompt a deeper search for other galaxies in its vicinity. That search can reveal that the region is not as empty as thought. This is a common outcome of follow-up. The object does not violate the void. It reveals a limitation in the original mapping. Therefore, the inward approach to a surprising object includes remapping the local environment with deeper data looking for faint companions and comparing with multiple void definitions. Only when the object remains isolated in the deep interior under these tests does the object become genuinely informative about the most underdense conditions. In calm terms, the void is a gradient landscape with edges, internal ridges, and three-dimensional projection effects. The placement of an object within this landscape is essential for judging whether it is merely rare, simply missed before, or genuinely unexpected. With boundary and internal structure handled, the next inward step is to explore the interior more directly, how the deep interior is structured in dark matter and gas, how slow flows and faint halos behave, and why certain measurements, especially absorption, can reveal interior content that emission surveys cannot. This step refines the environment around the object and narrows which physical explanations remain plausible. The deep interior of the Boötes Void is the regime where the underdensity is strongest, and where the local environment is most unlike the crowded walls of the cosmic web. Yet even here, structure exists at low contrast. Dark matter forms a sparse network of halos and faint filaments. Gas follows the gravitational landscape, but is also shaped by pressure and by ionizing radiation. The inward task at this stage is to describe what interior structure can reasonably exist, and how it can be detected, because an object in the deep interior is most often discovered by methods that are sensitive to faint traces rather than by bright emission alone. The deep interior is expected to have fewer massive halos. This means that the typical galaxy population is shifted toward lower mass systems. Many halos may host galaxies that are faint or diffuse. Some may host no visible galaxies because their gas is too warm and too diffuse to cool and form stars efficiently. This creates a landscape where mass can be present without obvious luminous markers. Therefore, a deep interior object might be a faint galaxy that has retained gas and formed stars slowly, or it might be an active nucleus in an isolated galaxy, or it might be a gas structure detected only in absorption. Each of these fits within known void interior structure. Dark matter substructure is a quiet foundation. It determines where gas can collect. In low-mass halos, the ultraviolet background can prevent gas from collapsing. Gas can remain in a warm ionized state. Yet some halos can cross thresholds where cooling becomes more effective, especially if some metals are present, and can form stars at low rates. Over long times, even a slow rate can build a detectable stellar component. In the absence of frequent interactions, disks can remain stable and extended. Therefore, deep interior galaxies can be physically large but faint per unit area. They can be missed by surveys that are optimized for high surface brightness. Deep imaging that carefully models the sky background can reveal such galaxies. Their presence is not an anomaly of physics. It is an outcome of the interaction between shallow potentials, slow gas accretion, and observational bias. Gas in the deep interior is mostly ionized and thin. Because emission scales strongly with density diffuse, interior gas emits very little in optical or X-ray bands. This is why void interiors are often studied through absorption. Absorption lines in the spectra of background quasars reveal intervening gas along narrow sightlines. A quasar behind the void provides a beam through the interior. If absorption is detected at redshifts corresponding to the void's distance range, it indicates that gas exists there. The existence of gas is expected. The interesting part is its state. Ionization modeling and line ratios can indicate whether the gas is photoionized, diffuse medium shock heated gas, or gas closer to a galaxy halo. In a deep interior, the absence of nearby bright galaxies can suggest a more diffuse origin, but faint galaxies can still exist and must be searched for. Therefore, a deep interior absorber can be interpreted as a probe of the void medium, with the caveat that unseen halos may contribute. The deep interior also hosts slow flows. Matter tends to move outward from the void interior toward the walls, but within the interior there can still be relative flows along faint filaments. Gas can accrete into halos gently. These flows can be too weak to produce strong shocks or bright emission, but they can shape the distribution of gas and create mild density ridges. These ridges can increase the likelihood of absorption. They can also slightly increase the likelihood of star formation in the halos along them. Therefore, a deep interior object might sit on one of these faint ridges. In that case, the object is not isolated in a perfectly uniform environment. It is part of the low contrast structure that voids are expected to contain. This again reduces the sense of impossibility. Energetic phenomena in the deep interior are rarer but possible. An active galactic nucleus requires gas inflow to a central black hole. Major mergers are less frequent in the deep interior, but internal instabilities and minor interactions can still drive inflow, and some galaxies may carry enough gas to feed the nucleus. If an active galaxy exists deep inside the void, its jets can expand into a low-density medium, potentially creating large radio lobes. Such lobes might be detectable even if the host galaxy is faint. The deep interior environment can allow lobes to grow large in physical size, but microphysical energy loss processes still limit their visibility. Therefore, a deep interior radio structure would imply either ongoing activity or relatively young electron populations constraints that can be tested by radio spectra. If such a structure were claimed without a host galaxy, the inward check would be to search for faint host candidates at the lobe center and to measure redshifts. Without that, the structure could be behind the void. The deep interior can also contain relic structures such as fossil radioplasma from past active galaxies or enriched gas pockets from ancient outflows. In low-density regions, mixing can be slow. A metal-enriched pocket can persist. A relic radioplasma can persist in a faint form, but becomes hard to detect because electrons cool. These relics can be found in sensitive surveys, but their interpretation requires caution. A relic signal can appear detached from obvious sources because the source is faint or has faded. Therefore, a deep interior object that appears sourceless can still be connected to a faint old or low-activity galaxy. This is not a new mechanism. It is a combination of slow evolution and observational limits. Another aspect of deep interior structure is the possibility of misclassification by projection. A region that appears deep interior in a coarse map may not be deep interior when faint galaxies are included. Deep mapping can reveal that the object sits in a modest overdensity relative to the interior average, such as a small filament. Therefore, an object that seems impossible under a simplified empty interior model may become plausible when the interior is mapped at higher resolution in tracer space. This is why deep interior claims often require follow-up that is deeper than the original void-defining survey. In calm terms, the deep interior of a void is a sparse landscape of small halos, thin ionized gas, faint ridges, and slow flows. It supports faint galaxies and absorption systems. It can support rare active nuclei and their relics, but these are uncommon. It does not naturally support bright widespread emission from hot dense gas. Therefore, if the claimed object implies high density and high temperature over large scales, the claim would demand strong evidence, and would likely indicate a background object or a misdefined void boundary. If the claimed object is a faint galaxy, a gas-rich system, an absorber, or a rare active system with a host, it can be consistent with the interior. The next inward step is to use chemistry and ionization as a finer tool for distinguishing among these possibilities, because the chemical and ionic signatures of gas can indicate whether an object is connected to a galaxy halo, to a faint filament, or to the more diffuse void medium, and can thus narrow the plausible physical origin of the object. Chemistry and ionization provide a way to narrow the identity of a void interior object without relying on dramatic language. In low-density environments, many of the most informative signals are not bright images but subtle spectral fingerprints. These fingerprints arise because atoms and ions absorb and emit light at specific wavelengths. The pattern of which lines appear, how strong they are, and how broad they are can indicate temperature density and enrichment. In a void interior, the key question is often whether a detected gas signal belongs to diffuse intergalactic medium, to a faint internal filament, or to the halo of a galaxy that may be faint or even undetected. Chemical and ionic clues help separate these possibilities. Hydrogen and helium are the dominant elements by abundance. They're created in the early universe. Heavier elements, called metals in astronomical language, are produced later in stars and spread into surrounding gas by winds and explosions. Because void interiors have fewer galaxies, the average metal enrichment is expected to be lower than in denser regions, yet enrichment can be patchy. A single small galaxy can enrich a region around it, and outflows can carry metals outward. Over long times, metals can travel and mix. Therefore, the presence of metals in a void interior is not inherently contradictory. What matters is the level and distribution of metallicity and the ionization state of the gas. Ionization state depends on the balance between ionization and recombination. In diffuse intergalactic gas, ionization is driven largely by the ultraviolet background, produced by galaxies and quasars across the universe. Recombination depends on electron density. In a void, electron density is low, so recombination is slow. This means gas can remain highly ionized. Hydrogen in diffuse void gas is mostly ionized, but a small neutral fraction can remain. That small fraction can produce measurable absorption lines, especially over long path lengths. Therefore, hydrogen absorption does not imply that the void contains neutral clouds filling space. It implies a measurable neutral column along a sightline. This is an important inward correction for any claim that treats absorption as evidence of unexpected density. Absorption is sensitive and void interiors are large. Metal absorption lines offer additional leverage because different ions trace different regimes. Some ions are common in photoionized gas at temperatures typical of tens of thousands of degrees. Other ions are associated with hotter gas and can indicate shock heating or collisionally ionized conditions. By measuring multiple ions, one can infer whether the gas is photoionized by the background, heated by shocks, or influenced by local sources. In a void interior, photoionized diffuse gas is expected. Shock-heated gas can exist along faint filaments and near halos. Gas influenced by local sources can exist near galaxies. Therefore, the ionic pattern can suggest proximity to galaxies even when the galaxy is faint. If the metallicity is relatively high, and the ion ratios resemble those typical of circumgalactic gas, the absorber is likely tied to a galaxy halo. If metallicity is low, and the pattern suggests diffuse photoionized gas, it may be more representative of the void medium. The distinction is not absolute because ionization modeling has uncertainties, but it narrows the plausible origin. Ionization modeling requires assumptions about the ultraviolet background spectrum and intensity. The background can vary with cosmic time and can vary modestly with environment. In a void, the local contribution from nearby galaxies is reduced, but distant sources still contribute. Therefore, the ultraviolet background is not absent, but it may be slightly lower locally. This uncertainty affects inferred densities. A given set of ion ratios can be explained by lower density under a stronger background, or higher density under a weaker background. Therefore, derived quantities such as gas density and metallicity often come with ranges. A careful statement notes what is constrained and what is sensitive to assumptions. This is not speculation, it is a bounded uncertainty. Metallicities themselves also have observational uncertainty, because they depend on column density estimates for hydrogen and metals and on ionization corrections. Yet even broad metallicity categories can be informative. Extremely low metallicity suggests minimal enrichment and a more pristine environment. Moderate metallicity suggests some enrichment, possibly from small galaxies or ancient outflows. Higher metallicity suggests proximity to a galaxy. In a void, the distribution might include all three, but with different frequencies. Therefore, if an object claim is based on a metal-bearing absorber, the inward follow-up is to search for galaxies near the absorber redshift. If a galaxy is found, the absorber likely traces its halo. If no galaxy is found to deep limits, the absorber may trace diffuse void gas or a halo of a very faint galaxy. The depth of the galaxy search is therefore part of the conclusion. Chemistry also matters for cooling and structure formation. Metals provide additional ways for gas to radiate energy and cool. In metal-poor gas cooling can be less efficient, making it harder for gas to condense into dense star-forming clouds. This can suppress star formation in low-mass halos, increasing the fraction of dark halos. In a void where halos are typically low mass, this effect can be important. Therefore, low metallicity environments can sustain long-lived diffuse gas and reduce the formation of luminous galaxies. This is consistent with the underdense nature of the void. Conversely, if a void galaxy exists and enriches its surroundings, the enriched gas can cool more efficiently locally, potentially supporting continued star formation and the formation of denser gas clouds. This creates patchiness. A void can contain pockets where enrichment and cooling have progressed. and large regions where gas remains diffuse. This patchiness can be revealed through absorption studies that sample different sightlines. Molecular signatures provide a sharper indicator of dense shielded gas. Molecules form efficiently in cold dense regions and are easily destroyed by ultraviolet radiation in diffuse regions. Therefore, strong molecular absorption or emission at the void distance would usually indicate gas within a galaxy, or very near it not diffuse void medium. Similarly, dust signatures such as strong reddening are more consistent with galaxy environments than with diffuse intergalactic space. Therefore, if an object claim involves molecular gas or strong dust effects inside the void, the inward implication is that a galaxy environment is present, perhaps faint and previously unrecognized. Emission line chemistry provides another tool when emission is detected. Emission lines require relatively high-density gas where collisions are frequent. In void interiors, such conditions are typically found within galaxies or in compact shocked regions near halos. Emission line ratios can indicate whether the gas is ionized by stars, by an active nucleus, or by shocks. This helps classify the energy source and the environment. If a claimed object is a diffuse emission region, emission line diagnostics can test whether it is truly diffuse void gas, or instead a galaxy-related phenomenon. Because emission from truly diffuse void gas is expected to be very faint, strong emission lines would usually point to a more local, denser origin. Another chemical clue comes from velocity structure. Absorption lines can show multiple components at slightly different velocities. Complex velocity structure often indicates multiple gas clouds, perhaps in a galaxy halo or in a filament intersecting multiple halos. Simpler structure can indicate more uniform diffuse gas. Again, this is not definitive, but it provides context. In calm terms, chemistry and ionization do not create a new story. They narrow the existing ones. They help separate void medium from halo gas, identify enrichment pathways, and constrain temperature and density regimes. For an object claim, these constraints can show whether the object is likely connected to a faint galaxy, to an internal filament, or to the broader diffuse medium. The next inward step is to examine formation and survival processes in the void. In light of these chemical constraints, how small galaxies can form and persist, how gas can be retained or expelled, how metals can be transported and mixed, and how energetic relics can remain detectable. Because these processes determine whether the object is an expected outcome of void evolution, or a rare event requiring special circumstances. Formation and survival inside the Boötes Void depend on slow assembly and gentle disruption. Gravity still gathers matter into halos, gas still responds to heating and cooling, stars still form where gas becomes dense and cold enough. Yet the void environment shifts the balance. The average density is low, so the supply of material is reduced. Massive halos are rarer, so deep gravitational wells are uncommon. Interactions between galaxies are less frequent, so the external triggers and disturbances common in denser regions occur less often. These conditions do not prevent structures from forming. They make certain outcomes less common, and they change the typical pathways by which an object can appear. A claim that an object should not exist becomes a question about process. What sequence of formation events could create it, and what processes would normally erase it? In the void interior, some structures are easier to form than assumed, while others are hard to sustain because they require density. Dark matter halos are the first stage of formation. In an underdense region, the spectrum of halos shifts toward lower masses. Many halos are small enough that they struggle to capture and retain gas once the ultraviolet background heats and ionizes the intergalactic medium. Warm ionized gas has pressure. In a shallow gravitational potential, that pressure can prevent gas from settling and cooling. This creates a population of halos with little or no star formation. Such halos are invisible in light, yet they are real structures. Therefore, an apparent contradiction between emptiness and the presence of mass can be resolved by the existence of dark halos. If an object claim involves a gravitational signal or dynamics suggesting mass formation by ordinary halo growth is plausible. The question is whether the mass scale implied is modest, which is expected, or very large, which is less expected deep inside. Gas accretion is the next process. Even in a void, gas can trickle along faint filaments into halos. Because the void is not entirely featureless, weak density ridges can guide inflow. In low-mass halos, accretion can be intermittent and slow. This slow supply can sustain low-level star formation over long times without producing a bright galaxy. It can also allow a galaxy to remain gas-rich because the rate of turning gas into stars can be low. A gas-rich galaxy detected by neutral hydrogen emission is therefore a plausible product of long-term accretion and retention in a quiet environment. Such a galaxy may appear to contradict an optical void map, but the process is consistent with void conditions. Star formation in the void tends to be sensitive to thresholds. To form stars, gas must cool and become dense. Cooling is aided by metals and by molecules, and molecules form more readily when dust is present and when gas is shielded from ultraviolet radiation. In small halos with low metallicity, cooling can be inefficient and star formation can be delayed or weak. When star formation does occur, feedback follows. Supernovae and stellar winds inject energy and momentum into the gas. In shallow halos, feedback can expel gas. In a low-pressure surrounding medium, expelled gas can expand farther before slowing. This makes gas loss more likely and makes the surrounding enrichment region potentially larger. Therefore, void galaxies can be chemically influential, despite being few, because their outflows can travel into the surrounding low-density medium. Metal-bearing absorption systems inside the void can be survivors of this process. Their survival depends on mixing and dilution. In low-density environments, mixing can be slow, and the enriched gas can remain in pockets and filaments for long times. This persistence can make metal absorption detectable along some sightlines even when the void is sparse. This does not require a high galaxy density. It requires time and occasional outflows. The formation of low-surface brightness galaxies is another process shaped by the void environment. In denser regions, repeated interactions and tidal forces can disturb disks, trigger bursts of star formation and strip gas. In a void, these external disturbances are rarer. Gas can settle into extended distributions. Star formation can proceed at low intensity across a large area. The result can be a physically large disk with faint surface brightness difficult to detect in shallow imaging. Such a galaxy can be the kind of object that seems not to belong in a void simply because the void was defined by objects that are easy to see. The formation pathway is ordinary disk growth in an isolated halo, with sustained gas supply and low interaction rates. The survival pathway is also ordinary fewer encounters mean fewer disruptive events. Therefore, these galaxies can persist longer and remain undisturbed, making them more likely to be missed and later found. Active galactic nuclei introduce another formation and survival pathway. Feeding a central black hole requires gas inflow to the inner regions of a galaxy. In denser environments, major mergers can drive such inflow, but they are not the only mechanism. Internal instabilities in disks, bars, minor interactions, and stochastic accretion can also provide fuel. In a void, major mergers are less frequent, but internal processes can still operate. Therefore, an active nucleus can form in an isolated void galaxy, though it may be less common. Once active, it can produce bright emission and jets. Jets can inflate radio lobes. In a low-density environment, lobes can expand more easily and reach large sizes. The survival of radio lobes is limited by radiative losses of relativistic electrons, and by expansion and mixing. Inverse Compton scattering on the cosmic microwave background drains electron energy everywhere, including in voids. This means old lobes fade. Therefore, a large radio structure in a void interior implies either that the activity is ongoing, that the lobes are relatively young, or that there is some mechanism for reacceleration. These conditions are not exotic, but they are constraints that can be tested. A radio object without a clear host can sometimes be a relic whose host is faint or whose core has faded, but it can also be a background object projected onto the void. Survival analysis therefore returns to distance anchoring and to spectral aging measurements. Shocks and gentle structure, formation processes can also create transient features. As matter flows outward from the void interior and along faint filaments, mild shocks can occur. These shocks can heat gas and may accelerate particles. In the void interior, gas density is low, so emission from heated gas is faint. Particle acceleration efficiency may also be low. Therefore, any diffuse emission from such shocks is expected to be difficult to detect and easy to confuse with foregrounds. If such a feature is confirmed, it would imply that internal filaments and magnetic fields are present at detectable levels, and that shocks are active. This would refine the picture of void interiors, but it would still be an outcome of known processes. The survival of such features would be limited by cooling and particle energy losses, making them transient and less continually driven. Another survival factor is time. In a quiet environment, some structures can persist longer simply because there are fewer external disturbances. Enriched gas pockets can remain unmixed. Low surface brightness disks can remain undisturbed. Small galaxy groups can remain loosely bound without frequent harassment. This longer persistence can make rare structures easier to find at a given moment, even if formation events are infrequent. Therefore, void interiors can contain relics and long-lived faint structures that are less common or harder to recognize in denser regions. In calm terms, formation and survival in the void can produce several classes of objects that might be described as not belonging gas-rich faint galaxies, large diffuse disks, enriched absorption systems far from obvious luminous galaxies, rare active nuclei with large radio structures and subtle internal filament features. None of these demands a break from established physics. They demand careful mapping of environment-secure distance placement, and realistic expectations shaped by tracer bias and observational limits. The next inward step is to describe how observers test an object claim, so that formation pathways are not chosen by preference, but by elimination, confirming distance checking for faint hosts and companions, verifying persistence across datasets, and comparing the detection to expected rarity given the surveyed volume and sensitivity. Testing whether an object truly belongs to the Boötes Void interior is an inward narrowing from appearance to evidence. The claim that it should not exist carries weight only if the object is real, if its distance is secure, if it lies within the void under robust definitions, and if its properties remain after the most common confusions are removed. This testing is not one step. It is a series of checks that reduce alternative explanations. In a void context, the dominant alternatives are distance misassignment, projection onto boundary filaments, foreground contamination, background confusion, and instrumental artifacts. When these are addressed, the remaining interpretation can be stated calmly as a constrained physical statement rather than as a paradox. The first and most decisive test is distance anchoring. For a compact object, spectroscopic redshift is the strongest anchor. A spectrum reveals identifiable features such as emission or absorption lines. Their shifted wavelengths give redshift. Once a redshift is measured, the object can be placed in three-dimensional context relative to the void's distance range. If the redshift lies outside the void interval, the object is not in the void. If it lies within the association, becomes plausible, but boundary definitions still matter. Distance anchoring also requires acknowledging that redshift includes peculiar velocity. In voids, peculiar velocities are typically smaller than those in clusters, but they still exist. Therefore, for objects near the void boundary, a small velocity can move them across the threshold. This is not a failure of measurement, it is a physical uncertainty. For diffuse features without clear spectral lines, anchoring is more difficult. In those cases, association with a host galaxy at known redshift becomes essential. If a diffuse radio lobe is claimed, the inward test is to identify a central host and measure its redshift. If a diffuse optical feature is claimed, the inward test is to search for resolved stellar populations if nearby, or for spectral signatures if possible, but often the practical approach is to tie the feature to galaxies embedded within it. Without anchors, the correct language is that the feature is in the direction of the void rather than inside it. Mapping the local environment is the second major test. If an object lies at the void distance, one asks whether it is truly isolated in a deep interior, or whether it sits on an internal filament or near a boundary ridge. This requires a three-dimensional map of nearby galaxies at similar redshifts. Modern surveys can provide many redshifts, but completeness can still be limited for faint galaxies. Therefore, the mapping often includes targeted follow-up spectroscopy and deep imaging. The inward goal is to measure the local density around the object relative to the void interior average. If the object is surrounded by a modest overdensity of faint galaxies, it may belong to an internal filament. If it sits near the edge where the density rises, it may be an edge object. If it remains isolated in deep data, then it is a stronger interior case. For absorption systems, the environment mapping is done by searching for galaxies near the sightline at the absorber redshift. If a galaxy is found at small projected separation, the absorber may be circumgalactic. If none is found down to deep limits, the absorber may be diffuse. The depth of the galaxy search becomes part of the uncertainty. Multi-wavelength confirmation is the third major test. A real astrophysical object has a set of expected counterparts depending on its nature. A star-forming galaxy typically emits in ultraviolet and infrared, and has characteristic optical colors. A gas-rich galaxy should show neutral hydrogen emission and may be faint in optical. An active nucleus should show distinctive spectral signatures and often emits in X-rays. Radio-loud nuclei show jet-related emission. A thermal plasma emits in X-rays with a characteristic spectrum. A synchrotron source has a radio spectrum and may show polarization. A dust-related foreground feature correlates with infrared cirrus maps. Therefore, the inward approach is to compare datasets across bands and instruments. If a diffuse optical feature is claimed, one checks whether it correlates with dust emission. If it does, it may be galactic. If it does not, and if it is associated with galaxies at the void, redshift, the extragalactic case strengthens. If a radio feature is claimed, one checks its spectrum across frequencies, its morphology, and whether it appears in independent surveys. If a claimed X-ray glow is present, one checks whether an optical cluster is present at the same position, and whether the X-ray spectrum indicates hot gas or a background of point sources. Robustness to processing choices is the fourth test, and is especially important for faint diffuse signals. In optical imaging, background subtraction and scattered light removal are critical. A feature must persist when reasonable variations of sky modelling are applied. It should not align with detector seams or known reflection patterns. In radio imaging, calibration choices and imaging weighting schemes can change the appearance of extended emission. A genuine structure should persist across these choices, and ideally across independent arrays and observing campaigns. In X-ray imaging, background modelling and point source masking are critical. A genuine diffuse feature should persist when background models are varied within uncertainty, and when point source contamination is controlled. These tests are often the difference between a stable detection and a fragile one. Confusion analysis is a fifth test. If a feature could be caused by many unresolved sources, one can estimate expected confusion noise based on source counts and instrument resolution. One can also test whether the residual emission has the spatial statistics of a point source field. Higher resolution follow-up can resolve sources and reduce confusion. In the void direction, confusion can be especially relevant because background sources behind the void are not suppressed. Therefore, the inward approach is to treat diffuse residuals with caution until confusion contributions are quantified. Physical parameter consistency is a sixth test. Once a signal is interpreted as a particular physical mechanism, the implied parameters should be plausible for a void environment. For thermal X-ray emission, the implied density and temperature should be consistent with a gravitational potential that can confine hot gas. If there is no mass evidence, a background cluster is more likely. For synchrotron emission, the implied electron energy distribution and cooling times should be consistent with the size and brightness of the feature. If the feature is too extended and too bright to be sustained, given electron cooling, ongoing injection or reacceleration must be present. If no source is identified, the interpretation becomes strained. For emission line regions, the implied gas density and ionizing radiation field should match the presence of stars or an active nucleus. For absorption systems, the implied density and metallicity should be consistent with either diffuse photoionized gas or circumgalactic gas, and the uncertainty from ionization modeling should be stated. Statistical expectation is a seventh test. A large void covers a large volume. Rare objects can occur by chance. Therefore, the inward approach compares the detection to expected space densities. If the expected number of such objects in the surveyed volume is not near zero, finding one is not surprising. If it is extremely low, the evidence threshold must be higher. This test does not require exact calculation in every case, but it requires a sense of scale. It prevents the word impossible from being used when rare is enough. In calm terms, testing is a structured elimination of alternatives. Distance anchoring places the object in 3 dimensions. Environment mapping checks whether it is truly interior. Multi-wavelength confirmation and processing robustness check whether it is real and of the claimed nature. Confusion analysis checks whether it is a blend. Physical parameter consistency checks whether the interpretation fits known mechanisms under void conditions. Statistical expectation checks whether rarity alone can explain the impression. After these tests, the object can be described as a particular physical system in a particular environment with bounded uncertainty. The next inward step is to examine the microscale mechanisms that connect a confirmed signal to its cause, because once the object is stabilized in location and reality, the decisive question becomes whether its detailed spectral and morphological properties match the microphysics of atoms, plasma's dust and energetic particles, and whether those microphysics impose constraints that narrow the remaining explanations. Microscale mechanisms translate a detected signal into a physical condition. They operate at the level of atoms, ions, electrons, dust grains, and the statistical behavior of detectors. In a void setting, these mechanisms are especially important because the signals are often faint and ambiguous. Microphysics can help discriminate between diffuse intergalactic gas and galaxy halo gas, between synchrotron emission and blended backgrounds, between thermal plasma emission and point source contamination, and between true extragalactic low surface brightness features and galactic dust scattering. The inward task at this stage is to describe these mechanisms in a way that ties each to specific observable signatures and to the constraints they impose. If those constraints are satisfied, an object becomes plausible. If they are not, the interpretation becomes strained and alternatives regain weight. Absorption line microphysics begins with atomic transitions. An absorption line appears when atoms or ions in intervening gas absorb photons of a specific energy, removing light at a specific wavelength. The strength of the line depends on the number of absorbers along the path called column density, and on the fraction of the element in the relevant ionization state. The width of the line depends on thermal motion and on velocity structure. Thermal motion broadens lines because hotter gas has faster moving particles. Velocity structure broadens lines because multiple clouds or flows at different velocities contribute. By measuring multiple lines from the same element and from different elements, one can infer whether the gas is photoionized by ultraviolet background radiation or collisionally ionized at higher temperatures. In photoionized gas, ionization is driven by photons, and temperature can remain moderate. In collisionally ionized gas, temperature must be high enough for collisions to strip electrons. In a void interior, diffuse photoionized gas is expected. Shock-heated gas may occur along filaments and around halos. Therefore, if a void object claim is based on absorption, microphysics helps locate the gas on this spectrum. It also sets constraints on density. In low density, gas recombination is slow, so ionization remains high. Ionization modeling often yields a range of densities depending on assumptions about the ultraviolet background. That range can still discriminate between a galaxy halo density and a much lower diffuse intergalactic density. A model becomes strained if it requires very high density without a nearby galaxy or halo, or if it requires a radiation field far above the expected background without a local source. Emission line microphysics differs because emission often depends on collisions. In ionized gas, electrons collide with ions exciting them, and then the ions emit photons as they return to lower energy states. Emissivity often scales with the square of density, because collisions require two particles to meet. This is a powerful constraint. Diffuse gas at void densities has very low emissivity. Therefore, detectable emission lines generally indicate denser gas, typically in galaxies or in compact shock regions. Emission line ratios can indicate the ionization source. Hot young stars produce a different ionizing spectrum than an active nucleus, and shocks produce distinctive ratios as well. Therefore, if an object is a patch of emission in the void direction, microphysics can test whether it is consistent with star formation, active nucleus activity or shocks, and whether the density implied is plausible for a void interior without a confining gravitational well. A broad bright emission feature spread over large scales becomes strained because it would require either high density over large volumes or a strong ionizing field distributed widely, both unlikely in a void interior. Synchrotron microphysics involves relativistic electrons and magnetic fields. An electron spiraling around a magnetic field line emits radiation, with a characteristic spectrum that depends on electron energy distribution and magnetic field strength. The observed radio spectrum, often approximated by a power law over certain ranges, can be measured across frequencies. The slope, called spectral index, indicates how electron energies are distributed and whether the population has aged. Electrons lose energy through synchrotron emission and through inverse Compton scattering on background photons. Inverse Compton losses against the cosmic microwave background are important because the cosmic microwave background fills space uniformly. This means that even in the emptiest void, electrons cool. Cooling causes higher energy electrons to fade faster, steepening the spectrum. Therefore, a large radio structure has a microphysical clock. If it is very large and yet has a relatively flat spectrum, it likely has recent or ongoing particle injection. If it has a steep spectrum, it may be older. Polarization provides another microphysical clue. Synchrotron emission can be polarized if the magnetic field has order. Measuring polarization can support a synchrotron interpretation and can reveal field structure. In a void where the surrounding medium is low density, a radio lobe can expand, but the microphysical constraints still apply. A claimed diffuse radio object becomes strained if it requires electron lifetimes much longer than allowed, without evidence of reacceleration, or if its spectrum and morphology match galactic foregrounds better than extragalactic structures. Thermal plasma microphysics governs X-ray emission. Hot ionized gas emits X-rays through thermal Bremsstrahlung, the radiation produced when electrons are deflected by ions, and through line emission from highly ionized metals at certain temperatures. The X-ray spectrum can be fitted to infer temperature. Brightness and spectrum together constrain density and total gas mass. Because emissivity scales with density squared, extended bright X-ray emission typically implies relatively dense gas, which is usually found in galaxy groups and clusters, where gravity confines hot gas. In a void interior, such deep potentials are rare. Therefore, if a claimed X-ray object is placed in the void, microphysics demands a matching mass distribution. If lensing and galaxy dynamics do not show a sufficient potential, well, a thermal plasma interpretation becomes strained, and alternatives such as a background cluster or unresolved point sources become more plausible. Microphysics can also discriminate between thermal emission and a non-thermal power law spectrum typical of active nuclei. Dust microphysics includes scattering and thermal emission. Scattering efficiency depends on grain size and wavelength, producing a characteristic color dependence. Dust emission depends on grain temperature and composition, producing infrared spectra. If a diffuse optical glow is claimed, checking its colors and correlation with infrared dust maps can test whether it is scattered starlight from Milky Way dust, if it is the object is foreground, if it is not, and if it aligns with galaxies at a consistent redshift. Extragalactic interpretations gain weight. At extreme faintness measurement, microphysics matters as much as astrophysical microphysics. Detector noise background modeling and systematic errors set the floor of what can be trusted. A feature detected near that floor must be stable against reasonable analysis changes and must appear in independent datasets. Otherwise, microphysics of the detector, not the sky, is shaping the signal. In calm terms, microscale mechanisms provide signatures and constraints. Absorption lines constrain column density, ionization, and temperature. Emission lines constrain density and ionization source. Synchrotron emission constrains electron populations, magnetic fields, and age. X-ray emission constrains temperature density and mass confinement. Dust scattering and emission constrain whether a feature is galactic. Instrumental microphysics constrains robustness. When an object claim is examined through these mechanisms, the word "should not exist" becomes a set of testable statements. Either the object fits within known microphysics, and the void environment, in which case it is a rare or previously missed member of an allowed class, or it demands parameters that are not supported by the void's mass and radiation context, in which case distance placement or interpretation is likely incorrect. The next inward step is to state the constrained implications of a confirmed object in the Boötes Void, to separate rarity from contradiction, to describe what would truly be unusual if confirmed deep inside, and to end with what remains uncertain, and how it can be reduced without making meaning from the result beyond its physical constraints. The innermost layer of the Boötes Void object claim is what remains after every outward layer is stripped away. The map of the void becomes a three-dimensional density field rather than a label on the sky. The object becomes a specific measurable signal rather than a dramatic phrase. The path from source to instrument becomes a chain of foregrounds, backgrounds, and processing steps that can be tested and repeated. When these reductions are made, the statement that an object should not exist separates into quiet conditional statements. If the signal is real in more than one dataset, if it is placed securely at the void distance, and if it lies within the void interior under more than one void definition, then the object is an example of what void interiors contain. The remaining question is what category of object it is and which constraints it satisfies. A void is a low-density environment, not a prohibited one. Under that, baseline rarity is expected. The innermost work is to separate rarity from contradiction without adding interpretation beyond what constraints support. A confirmed compact galaxy inside the void interior implies that at least one halo in the underdense region crosses the conditions needed to gather gas, cool it, and form stars. This is consistent with structure formation in an underdense field where small halos are common and where a smaller fraction of halos form luminous galaxies. If the galaxy is faint gas-rich or low surface brightness, the implication is often that earlier maps of emptiness were maps of bright traces rather than maps of all matter. If the galaxy is unexpectedly large or unusually diffuse, the implication is that quiet environments can preserve extended disks and allow slow star formation across wide areas, producing light that is hard to detect in shallow surveys. In that case, the object does not violate the void concept. It reveals the importance of surface brightness limits and the range of outcomes for isolated disk growth. If the object is an association of several faint galaxies, the implication is that the void interior contains internal ridges or filaments of slightly higher density consistent with the expected low-contrast structure in underdense regions. The group is then a sign of substructure rather than a collapse of the void picture. A confirmed active galaxy at the void distance implies that black hole feeding can occur in an isolated system. The environment may reduce the frequency of such activity, but it does not eliminate it. If radio jets and lobes are present, their size may be enhanced by the low-density surroundings, because the outflow meets less resistance as it expands. The microphysical constraint remains that relativistic electrons lose energy over time, including through scattering on the cosmic microwave background. Therefore, if the radio structure is large and bright, it implies either recent activity, ongoing activity, or an arrangement in which particle acceleration continues at a level consistent with the observed spectrum. None of these requirements breaks established mechanisms. They specify a subset of plausible histories. If the object is an absorption system at the void, redshift, the existence of diffuse gas along the sightline, is consistent with the baseline that voids contain ionized hydrogen and helium. The interesting constraint becomes the gas state. If the absorber shows low metallicity and ion ratios consistent with photoionization by the ultraviolet background, it points to diffuse void medium with modest enrichment. If it shows higher metallicity or ion patterns typical of galaxy halos, it points to circumgalactic gas, meaning gas near a galaxy, which may be faint and requires targeted searches. The key uncertainty is completeness. If deep imaging and spectroscopy fail to find galaxies near the sightline down to stringent limits, the circumgalactic explanation becomes less likely but not impossible, because very faint galaxies can still exist. The constrained statement becomes that the absorber traces gas in an underdense environment with bounded ranges of density and metallicity that depend on ultraviolet background assumptions. This is a refinement of void gas properties rather than a contradiction of the void. If the object is diffuse emission constraints become sharper. Diffuse optical light at very low surface brightness requires careful exclusion of galactic dust scattering and instrumental backgrounds. A confirmed extragalactic diffuse optical structure at the void distance would most likely be tied to a galaxy, a group, or a filament, where density is higher than the void mean because emission and starlight both require concentrated material. A truly volume-filling optical glow inside the deep interior is not expected, because the interior does not contain enough stars spread through space to create such light. Therefore, if diffuse optical emission is claimed without associated galaxies, the dominant uncertainties remain distance anchoring and foreground separation. In radio, diffuse synchrotron emission, not tied to a clear active galaxy, must overcome the combined constraints of low expected emissivity, strong galactic foregrounds and electron cooling. If such a feature is confirmed and if it is placed at the void distance, it implies internal filament shocks or relic plasma supported by magnetic fields and recent or ongoing particle acceleration. This would constrain void magnetization and the presence of internal filaments. It remains within known physical processes, but it would be a valuable measurement because it probes a regime that is hard to access. In X-rays, diffuse thermal emission implies hot gas with density high enough to radiate. Hot gas of group or cluster type is normally confined by a deep gravitational potential. A void interior is not expected to host many such potentials. Therefore, a confirmed extended X-ray halo at the void distance would require matching mass evidence. Weak lensing galaxy dynamics or a galaxy population at the same redshift would be expected to support it. If mass evidence is absent, a background cluster becomes more plausible, because background clusters are common enough to appear in projection. If distance anchoring and mass evidence both support a void interior hot gas structure, then the statement becomes that a significant mass concentration exists within an underdense region, defined by luminous traces, which points back to tracer bias and to the need for mass-based void definitions in that volume. This remains an extreme case. It is one of the few categories that could create genuine tension with simplified expectations, not by breaking laws, but by challenging assumptions about how empty a luminous void is in mass, and how likely high mass systems are within it. The phrase "should not exist" is most often a sign that an expectation has been applied without specifying the probability scale. A void covers a large volume. Large volumes contain rare systems. A rare system can appear startling when it is framed against the image of emptiness yet remain consistent with statistics. The innermost discipline is to express the claim as a question of frequency and of selection. How many objects of this class are expected in a volume of this size under the measured underdensity? How complete is the survey to the relevant class? How stable is the void boundary under deeper tracers? These questions remain technical, but they do not require embellishment. They decide whether the object is simply a rare occupant, a previously missed occupant, a misassigned background occupant, or a sign that the void definition used is incomplete for the physics being inferred. What would be truly unusual if confirmed deep inside the Boötes Void interior is not the presence of a faint galaxy or thin gas. It is the presence of a massive dense system that requires a deep gravitational well and dense hot plasma without corresponding mass evidence and without a surrounding galaxy population at the same distance. Another unusual outcome would be a strong widespread diffuse emission signal that requires densities and energy injection inconsistent with low-density gas while also surviving every foreground and instrumental test. These are narrow cases. They demand the strongest evidence because they sit closest to the edge where interpretation can be led by projection and by systematics. Even in these cases, the first practical response is not a leap to new mechanisms, but a return to distance anchoring multi-wavelength confirmation and mass measurements. The final inner statement is therefore constrained. A confirmed object in the Boötes Void does not erase the void. It places a concrete example within an underdense environment and tightens the description of what that environment contains. Remaining uncertainty usually lies in one of three places. The first is distance and boundary, meaning whether the object is truly deep interior or near an edge ridge when mapped with deeper tracers. The second is completeness, meaning whether faint galaxies and faint companions have been searched for to a depth that matches the claim. The third is mechanism, meaning whether the detailed spectral and morphological signatures match the microphysics expected for the proposed interpretation. When these three uncertainties are reduced, the object becomes a stable part of the void's inventory. The void remains an underdense region within the cosmic web, and the object becomes a measured occupant of that regime. After this, the script moves into the wind down in the same tone, letting the constraint settle without adding further claims. In the quiet volume mapped as the Boötes Void, the view remains wide and slow. The surveys trace bright galaxies first, and the map looks sparse. Deeper tracers add faint galaxies, thin gas, and subtle ridges in the density field. The space does not become crowded. It becomes better described. A claimed object becomes less a surprise and more a specific signal that either anchors to the void distance or does not, either survives repeated tests or fades under them, either matches known microphysics or requires a different classification. In that process, language softens into measurement. The void remains underdense with boundaries that are gradients rather than walls, and with an interior that contains dark matter structure and ionized gas that is hard to see in emission. The object, when real and well placed, becomes part of that interior catalogue, whether it is a faint galaxy, a gas-rich system, an absorption signature, or a rare energetic source. The remaining unknowns stay bounded by what current instruments can separate, and they narrow when more sightlines, deeper maps and independent datasets are added. The sky holds the same direction, the distance range holds steady, and the quiet checks continue until the signal is simply what it is.